Have you ever pulled up behind a massive cement mixer at a red light and found yourself staring at its wheels? You count them out of habit. 2 at the front, 4 in the middle, and then, tucked just behind those, a clean extra axle with its tires hanging a few inches above the road, not rolling, not touching, just floating there, perfectly still, while everything around it rumbles and vibrates. Your first thought is that something is broken. An axle has collapsed, maybe, or a hydraulic line has failed somewhere underneath all that steel. But the truck is moving fine. The driver seems completely unconcerned. So what exactly is happening underneath that machine? Across the world, heavy vehicles collectively cause the overwhelming majority of all road surface damage. Infrastructure agencies estimate that a single fully loaded articulated truck does roughly the same damage to a road as 10,000 ordinary cars making the same journey. The difference isn't just weight, it's how that weight lands. But here's the surprising truth. That floating wheel isn't a failure, it's a switch. A deliberate, engineered decision that the driver made a few minutes ago, and one they'll reverse the moment the load demands it. Today, we're unpacking why some trucks are built to lift their own axles off the ground, where the science behind road damage actually comes from, and why governments, engineers, and truck operators have been fighting over this problem for longer than the internal combustion engine has existed. To understand this properly, we have to go back to long before the motorway. Roads have always had a breaking point. Roman engineers discovered it when they watched heavily laden ox carts turn their carefully laid stone roads into rubble within a single season. Medieval towns tried taxing wagons by width, reasoning that wider wheels distributed weight better and caused less damage to the unpaved roads everyone shared. They were right about the physics, even if enforcement was nearly impossible. By the 19th century, when railways were making long-distance freight practical, the condition of road surfaces had become a serious political issue. Turnpike trusts in Britain and toll authorities across Europe experimented with weight limits, wheel width regulations, and surface materials, trying to solve a problem that always came back to the same fundamental equation. The heavier the load, the more force it concentrates on a small patch of surface, and eventually that surface gives way. When motor trucks arrived in the early 20th century, the problem became urgent. A steel-wheeled steam wagon or a rubber-tired lorry could destroy a road surface in a single pass that hundreds of horse-drawn carts had left intact for years. Governments began writing axle weight limits into law, not total vehicle weight limits, axle limits, because engineers understood that the damage came not from how heavy the truck was, but from how much of that weight pressed down on any single point. Think of it like pressing your fingertip into a piece of bread versus pressing your whole open palm down on it. The same force, completely different result. A loaded truck axle concentrates tons of weight into a strip of tire contact roughly the size of a sheet of paper. Multiply that force by highway speeds and thousands of daily passes, and even the most robust asphalt begins to crack and deform. This is called fatigue failure. Not a single catastrophic break, but a gradual accumulation of small deformations, each one invisible, until one day the road surface crumbles. The engineering solution was to spread that force across more axles, more tires, more contact points. Spread the palm wider. This is the lift axle. When a truck is empty, it runs light, and 2 or 3 standard axles handle the load within the legal limits perfectly well. The moment a driver loads up, that calculus changes. A fully laden aggregate truck might be carrying enough material to push a single axle load well beyond what the law permits. The driver flips a switch. Compressed air fills a set of pneumatic bags mounted above the extra axle, and the whole assembly drops until the tires meet the road. The truck now has more feet on the ground. The weight spreads. the legal limit is met. So if more tires touching the road protects the surface, why ever lift them again? The answer, as is often the case in history, comes down to what happens the moment the truck is no longer carrying anything. A tire rolling against road surface creates resistance. This is called rolling resistance, and it costs fuel. Every extra axle on the ground means more friction, more engine load, and more money spent on diesel over the course of a working day. Beyond fuel, tire wear is expensive, and beyond tire wear, there is a mechanical problem that almost nobody thinks about until something goes wrong. Trucks are long. When multiple fixed axles try to navigate a tight bend, the rear axles do not follow the front ones in a smooth arc. They drag sideways. This is called tire scrub, and on a sharp corner at a construction site or a loading dock, it can shred rubber off a tire in a single turn, stress the chassis, and tear up the road surface the whole system was designed to protect. A lifted axle removes that problem entirely. With fewer fixed points of contact, the truck pivots cleanly. It becomes, in a very real sense, a shorter vehicle. So, the next time you find yourself watching a truck at the lights with one axle hanging in the air above the road, you'll know that the driver didn't forget to lower something. They raised it deliberately, the way a pilot retracts the landing gear the moment the aircraft doesn't need it anymore, because carrying unnecessary contact with the ground has a cost. Sometimes the most useful part of a machine is the part that knows when to stop doing its job.